Oh, you can't see that, can you? Hang on here. There we go. So the topic of the day is implicit differentiation. This is a huge day in calculus. I really enjoy this day. This is a good, fun day you learn lots of great stuff. Let's start by providing some motivation for this, right? What if I give you something like z equals x times y, and I want you to calculate dz dt? How in the world are you going to do that, right? That's kind of a weird thing to ask. Well, we're going to talk about that today. Let's start off with just a little bit of review. Okay, let's find the tangent line when x equals 3, y equals x squared. Well, what would I do here if I want to find the equation of the tangent line? Andy, what am I going to do here?
You find the derivative.
Okay, so we get y prime, and this is an easy derivative, right? Y prime would just equal 2x, and keep going. Now what?
You have to plug in x equals 3 into the equation to get like a y value.
Okay, so if I plug 3 into the function, y would equal 9, right?
Mm-hmm.
So I end up with the ordered pair 3, 9, and that's going to be my point of tangency. And then what else? What else do I need with this?
And then if you plug x equals 3 into y prime, then you get the slope of the line.
Okay, good. So the slope of the tangent line would be 6. And now I've got everything I need, right? I've got a slope, I've got a point. All I've got to do is just use the point slope form. So y minus 9 equals m, which is 6 times the quantity x minus 3, and I'm done. I could, if I want to put that in slope-intercept form, we can do that. No big deal. Easy, right? We can do that stuff. Now, how about this one, though? A little different. Y squared equals x. Find the tangent line when x equals 9. Okay, what's the problem here? What's different and more difficult about this one? What do you think, Andrew? Okay, yeah, the y is not isolated, right? The y is a part of a power function. It's inside of a power function. I have a y squared there. Okay, that's a little more difficult because if I want to find the tangent line when x equals 9, well, y squared equals x, it really doesn't just look like that square root function, right? And you might be thinking I can square root both sides and get y equals the square root of x. But if I square root both sides of an equation, remember that I actually get 2 different answers. I'd get y equals plus or minus the square root of x. And so this ends up being a horizontal parabola, doesn't it? Right? And you notice here that there are 2 different places where x equals 9. And so when it says find the tangent line, that's a little misleading. There actually would be 2 tangent lines, wouldn't there? There'd be a line tangent to the curve at the point 9,3 and another line tangent to the curve down here at the point 9, -3, right? So that increases the complexity. And, you might be thinking, and you'd be correct in this case, we could do it this way. We could just break this up into 2 separate functions. I could do the top function, y equals the square root of x, and the bottom function, y equals negative the square root of x. And I could find both of those tangent lines independently the way I did with this one, right? Wouldn't be a big deal to do that, okay? Everybody see my point there? How we could do that? Okay, however, that's not always going to work. Here's an example of a function that I can't apply that strategy to. I cannot isolate y. It's algebraically impossible in this equation to solve for y. So I can't isolate y, and then differentiate. So I've got to come up with a different strategy if I want to be able to deal with derivatives of this function. And I should be able to, because let's try graphing this thing. If I graph this function, it looks a little bit strange. You notice there's some parts down here where I get some strange behavior, but this function does have a graph. So I should be able to find derivatives at places on this function where the function exists, right? Everybody understand the issue we're dealing with then, though, right? I can't solve this the way I was going to solve this guy, which would be using an explicit process. What do we mean by explicit? Well, an explicit process in math means one where I can explicitly solve for a variable and then do stuff with it, right? So in this case, we would solve this problem that I posed to you by explicitly solving for y and getting two different functions and then differentiating each of those to enable me to find slopes, right? That's an explicit process. It worked here, but it does not work for the equation in yellow. So we got to see if we can come up with a different, better way of doing this. Okay, well, let's go through this process first of all. So we already identified that we can use an explicit process here. We end up with the two equations. One of them was y equals the square root of x, and the other one was y equals negative the square root of x. Well, let's go through this process. If I differentiate both of these, this is just x to the 1/2, correct? So Caleb, what does this derivative give me if I differentiate that? I get y prime equals what?
1/2 x to the negative 1/2.
Okay, so same as 1/2 times the square root of x?
Yes.
Okay, how about this one over here?
Wouldn't that just be the same derivative but negative?
Yeah, negative 1/2 times the square root of x. Okay, and I could go from there, right? I want to know, do you see something here, anybody, that would be helpful? Do you see the original function y equals the square root of x or y equals negative the square root of x popping up in my solutions here? That's a pretty big hint. So that was my explicit process. Now notice in the red column here, y is defined as the square root of x. So would you agree that that's a y right there, isn't it? That part right there is just a y. So I could write my answer as y prime equals 1/2y. How about over here? Well, this time y equals negative the square root of x, right? That's how y is defined. I could reorganize this. I've got a negative 1/2 times the square root of x. Well, I've only got one negative there. I could attach that to any of these three factors, and I'd still end up with a negative quotient, right? So let's rewrite it this way. What if I rewrote that as y prime equals 1/2 times the quantity negative the square root of x? That's just a y, isn't it? Well, look, I got the same result I got over here then. I end up with y prime equals 1 over 2y. That's pretty slick. I got the same answer when I differentiated both of these two equations, right? So now my question is, could I have gotten there without having to go through the hassle of explicitly solving for y? Could I have just started with y squared equals x and gotten to the same place? Yeah. What if I just differentiate implicitly, which means I'm just going to differentiate all parts of my equation with respect to x and apply the chain rule? Okay. So what's that going to give me? On the left side, I'm just going to get the derivative with respect to x of y squared. On the right side, I'm going to get the derivative with respect to x of x. Well, what's the derivative of x with respect to x? That's an easy one. We've done that for a while. What's that equal to? 1. There we go. Good. So I'm getting a 1 over here. Now, what about this side? This is a two-layer problem, isn't it? Right? I'm taking the derivative with respect to x of y, or call it hand, squared. What's the derivative, first of all, of something squared? That's just 2 something to the 1, right? So I'm going to get a 2y to the 1 times the derivative of what's inside. Okay, well, the derivative of y with respect to x is not 1. Oh, sorry, that's not supposed to be a prime. It looks like a prime, but it's a 1. I'm going to get rid of that because it looks like it. You see what I'm saying? We don't want that to be. It's just 2 times y. I get 2 times y for the first layer of my chain rule. That's the first link. And then the second link, if I differentiate what's inside the power, it's just a y, dy dx. I'm just going to call that y prime. Anybody see that? Okay, now if I solve for y prime, I'm just going to divide each side by 2y, and look what I get. Y prime equals 1 over 2y. Well, that's the same thing that I got over here, going through a much more difficult and tedious process, right? So the moral of the story is we no longer have to explicitly solve for y when we want to calculate y prime. We can just leave the equation as it is and differentiate with respect to x. And y primes will pop out via the chain rule if they exist. Okay, let's demonstrate. So, I mean, we just did this, right? The implicit process. Like if we wanted to, we already did all the work. I guess let's just show how this works. So y prime equals 1 over 2y, right? We took the derivative implicitly, and we got y prime equals 1 over 2y. What if we wanted to solve our original equation and we wanted to find the tangent lines, right? Well, if we want to find the tangent lines in the original, we want when x equals 9, right? Okay, well, if I want to find when x equals 9 in my original equation up here, if I'm going to let x equal 9, that gives me y squared equals 9. What are the two possible solutions if I solve for y? Well, if I square root both sides, I would get y equals plus or minus 3. So that's going to give me 2 points. X is equal to 9, and y could equal plus or minus 3. So I get both of these 2 points, right? Because this is not a function. These points line up vertically, but there are two different points with x coordinates of 9. What about my derivative? Well, y prime equals 1 over 2y. Let's apply that to this point up here. If I apply it to this point, y prime would equal 1 over 2 times this y value is 3, right? At this point, y is equal to 3. So I end up with my slope is 1/6. What about down here? What about this guy? Okay, well now down here, y prime equals 1 over 2 times y, but in this case, y is -3, so I get a slope of -1/6. Look how easy that is using the implicit process to get there much faster. Okay, give me 1 to 5 real quick. Okay, we need a little more practice for sure. Yeah. Okay, let's go ahead. You know, I'm going to skip up and do this example first before we backtrack. So let's find y prime when x equals 1 for this relation, x squared plus y squared equals 4, which is just the equation of a circle with radius 2 centered on the origin. Okay, if I want to find y prime, I don't want to solve this thing for y explicitly. Let's just implicitly differentiate with respect to x. What's that going to give me? Let's just look at this term by term. What am I going to get from the first term? That's an easy one. If I differentiate with respect to x. What's that going to give me, Daisy? What's the derivative of x squared with respect to x?
2x.
2x. We don't really need to use the chain rule there, do we? Because we're differentiating with respect to x. Now, could we apply the chain rule? Yeah, we could. I want to just show that to you, right? If we're differentiating x squared with respect to x, well, I could treat this like a chain rule situation with two links. I've got a power function, so the derivative of hand squared is 2 times hand times the derivative of what's inside. Well, the derivative of x with respect to x is just 1, right? So there's really no reason to apply the chain rule there because we're differentiating with respect to x, and it's a function of x. But we could, if we really wanted to, we could apply the chain rule there. Just kind of a waste of time. Okay, so that's going to give us 2x. What about the next term over here? Plus y squared. What's the derivative of y squared with respect to x? And I'm going to have to apply chain rule. David, what are you going to get there?
I'm sorry, I was cutting out. What did you ask?
I want to know what's the derivative of this term. We're just differentiating this whole equation implicitly with respect to x. So now we did the first term. Now we want this second term. What's the derivative of y squared with respect to x?
Is it 2y?
2y, that's the outer layer, right? The derivative of something squared is 2 times something times what?
I don't know.
What's the derivative of the inside of that, Amber? Derivative of y squared with respect to x we're trying to find. Questions to Amber. Might be a technical issue. Emma, how about you? Y prime. Yeah, exactly. Right? The derivative of something squared is 2 times something. The derivative of what's inside, the derivative of y with respect to x, there's my y prime. Okay? Equals, what's the derivative of 4, everybody? Show me with your hand there. I'm seeing a lot of zeros. There we go. Okay? So I did the calculus. Right now, all I've got to do is solve for y prime. I could divide both sides by 2 and just get rid of those 2's, right? And then I just end up with x plus y prime equals 0. Well, if I want to solve for y prime, then y prime would just equal, let's see, I'm going to subtract the x and divide by y, right? So I just get negative x over y. There's my derivative. Is it alarming that I get x's and y's in my answer? No. We should expect that when we use an implicit process. I'm expecting to get x's and y's in my answer. And in this case, it makes sense that I would, because this is not a function. For every x value, there are multiple y values, right? So I need to specify, like if I want to find y prime when x equals 1, well, look at this. When x equals 1, I've got 2 different points. I've got a point right there, which has an x coordinate of 1, and I have a point right there with an x coordinate of 1. I don't know what the y values are. I mean, I'll need to find out, I guess, if I want to plug values into my function there, or into my derivative. But we could do that. If x is 1, I could take this original equation up here and solve it. So here it is. When x is 1, I just get 1 squared plus y squared equals 4. I can just solve that for y. So y squared would equal 3. So y would equal plus or minus the square root of 3. Well, that must be plus the square root of 3. And that must be minus the square root of 3, right? So those are my 2 points. Okay, those are my 2 points of tangency. And then if I want to evaluate the derivative there, whoops, what am I going to get? Well, if I take this top point up here, if I take that point, I'm just going to evaluate my derivative at those coordinates. So I would just get y prime equals negative. My x value is 1 divided by my y value is the square root of 3. So there's one derivative. What about down here at that point? Okay, at that point, I would get y equals negative. My x value is 1. My y value is negative radical 3. So the negatives cancel. Y prime would equal 1 over the square root of 3 instead of negative 1 over the square root of 3. Okay, everybody seeing that? Give me 1 to 5. Okay. Let's try another one. Oh, I forgot what did I have up here for layers? Oh, look at that. I even had my tangent lines drawn in. Okay, let's see this one. Let's find the slope of the tangent to the curve below at the point 2, 1. So this time the math gods are being nice to me. They're actually giving me the coordinates, both the x and y coordinates of the point of tangency. Okay. All right. So I want to take a second and just think about what your strategy is going to be here. Slope to the tangent to the curve. That's just the slope of the curve, right? Just the derivative. Just evaluating the derivative to find the slope of a tangent. So what do you think, Isaac? What's your strategy here?
Well, first find the derivative of the equation.
Okay. So what's that process called here? I'm going to, how would you describe this to somebody, what you're doing? I'm not solving for y, am I? It'd be difficult or impossible to solve for y there. So I'm not going to explicitly differentiate. What am I doing? There you go. I'm going to implicitly differentiate with respect to x, okay, to find y prime. Everybody see that strategy? Because any place, would you agree that any place I have a y, any term where there's a y, if you kind of look ahead, when I differentiate with respect to x by the chain rule, I'm always going to end up getting a y prime, aren't I? Hasn't that been our experience so far? Any term that has a y in it, when all the dust settles after doing all the layers of the chain rule, my last step is always going to be a y prime, isn't it? Look what happened on these last examples, right? That's what happened. I ended up getting, there was a term with a y in it. When I differentiated that term, last in, okay, same thing happened back here, right? When I differentiated implicitly, there was a term with a y in it. When I differentiated, I got a y prime. Okay, so that's how we're going to get those y primes, is implicitly differentiate with respect to x. So let's see what happens there. Let's just take these things term by term then. What am I going to get from the derivative of the first term? Isaac, what's that going to give me?
4x.
There you go, 4x. Okay, now this one's going to be a little bit trickier, right? That's a little trickier. Johan, what am I going to get from this second term here? What about this guy? We'll kind of color code this a little bit. So that one, when I differentiate that one, what am I going to get?
Would it be x times? I have no idea.
Well, that one looks a little tougher because it's a product, isn't it? I've got it. Everybody see I've got a product there. I've got, maybe we group the 3 with the x. So I could think of this as being 3x times y squared, right? I'm going to have to apply product rule, aren't I? Because I've got a product of functions there, product of factors. So let's try that. Let's apply the product rule there. You want to take a crack at it, Johan, or should I? You can pass if you want to.
Yeah, sure. I'll take a crack at it.
Okay.
So 3x times 2y.
Okay, I'm going to get 3x times, now I've got to do times the derivative of the second term, y squared. Okay, so that's going to give me 2y. Am I done?
Times y prime.
There you go, times y prime. Okay, now that's only the first term in the product rule though, right? Now I've got to go over and go plus. Second term is going to be, now I've got the second factor times the derivative of the first. Well, what's the derivative of the first?
Just x. I mean 1, right?
Well, but if we're saying 3, there you go, 3. There you go, good, 3. Okay, so that whole thing right there, that's the derivative of the second term, because we get 2 terms out of it because we had to apply product rule. Okay, so far 1 to 5 on that. We go thumbs up, thumbs down, thumbs sideways. We good on that? Okay. I mean, there's a lot going on here. Let's try this next one. This one, it's going to be this color. So now we're dealing with that term. Okay. Well, the way I'm going to handle that, I'm subtracting this other term. So I'm going to put a minus there. And I might as well just open up a big quantity, because I'm going to have to apply the product rule again, aren't I? Right? This time, let's group, how about the 2x squared? Let's group that together, and then the y by itself. Okay, so Kirsten, we got a product here. We're using the product rule, the product of 2x squared times y. And we're subtracting whatever we get from that product rule. So take the first part of the product rule then. What's that going to give me?
4x.
Okay, times.
What is the y term?
Well, I've got a 2x squared times a y. So I'm multiplying 2 things together. We just arbitrarily stuck the 2 with the x squared. Right, so I've got the product of the factor 2x squared times the factor y, right? And so I'm going to apply the product rule. And remember, the product rule is just like, here, let's do it this way. How about if we're just consistent? We'll use the same order. What you're doing was fine. But let's do what Johann did just to keep it consistent. He did the first times the derivative of the second plus the second times the derivative of the first. So we'll use this, apply the same kind of a pattern here. Right? So we're going to get our first was 2x squared. What's the derivative of y with respect to x?
Y prime.
Y prime. So there's my y prime. Good. Plus the second, which is y, times the derivative of the first. Well, what's the derivative of 2x squared?
4x.
4x. Okay, and we got it, right? There's the derivative. We implicitly differentiated with respect to x, that third term. Okay, now how about this guy right here? That's going to be an easier one, right? The derivative, I don't need a product or anything there. Kyle, what's that going to give me if I differentiate 4y cubed with respect to x? Oops, I can't hear you, Kyle. Your mic's not on. Still can't hear you, Kyle. Your mic's not on. We're skipping you, Kyle. You're having technical issues here. Lily.
12y squared.
12y squared. Okay, good. And then what's the next link in the chain going to be?
There's a y prime, but since it's squared, do you have to multiply it?
We do because we're doing two different layers here, right? I've got the derivative of 4 times hand cubed is 12 hand squared, right? Times the derivative of what's inside the power, which is a y. So there's my y prime. Anytime I've got a y in a term that I'm differentiating, I can guarantee I'm always going to get a y prime coming out of that by the chain rule if I'm differentiating with respect to x. And then finally, on the other side of this thing, the derivative of 10, derivative of a constant, is just 0. Okay, so look what that did then. That gave me a whole string of terms. And if I want to find the slope of the tangent, so I'm just finding y prime at this point, all I've got to do now is just solve for y prime. It looks like that's going to be terrible, but it's not, because look, the y primes are all linear. They're not taking any powers or anything. I've just got a y prime in some terms, and in some terms I don't. So if I want to isolate the y prime, wouldn't I just collect all the y prime terms on one side, push all of the non-y prime terms to the other side, right? And then factor out a y prime and divide the rest away, right? So let's go through that process. That sounds like a lot of stuff. Let's take the y prime terms and put all of them on the left. Well, here's a y prime term. This one's going to give me 2 times 3 is 6 xy y prime. Here's another y prime term right here. Right, that one's going to give me minus 2x squared y prime. And here's another one right here. Plus 12y squared y prime equals everything else we're going to push to the other side, right? So this one right here goes over there, right? And that's just going to give us a minus 4x. We're going to subtract it to this side. This one right here will subtract to the other side, and we'll get a minus 3y squared. And this term right here, this is already negative, isn't it? Right? So we're going to subtract. we're going to add that term to both sides, because when I distribute the negative, it becomes negative. And so we end up with a plus 4xy. Well, now to solve for y prime, wouldn't I just factor y prime out of this side? If I do that, if I factor out or undistribute a y prime, I'm just left with 6xy minus 2x squared plus 12y squared. And then I've already got all this stuff over here. Let's put the positive term first. So we just get 4xy minus 4x minus 3y squared. And then all I have to do is just divide each side through by this whole factor. And look what happens, right? Those cancel, and I got my answer, right? I get y prime equals all that stuff. It looks terrible, but who cares? That's the answer. That's what we get. We want to evaluate this when x is 2 and y is 1. That's easy. Just plug in 2 for x and 1 for y, and we get a number, right? So at 2, 1, y prime just equals, let's just figure what these are out term by term. So 4 times 2 times 1 is 8, minus 4 times 2 is 8, minus 3 times 1 squared is minus 3, over 6 times 2 times 1 is 12, minus 2 times 2 squared is minus 8, plus 12 times 1 squared is plus 12, and I get an answer of negative 3 over, what, 16? There it is. Okay. That looked like that was going to be a terrible problem, but it's not really that bad. Now, I would suggest, too, that you can really trim the algebra down here. You guys are smart enough that you can do some good mental math here. I would say, I'm glad you're not in the room, so you're not going to throw things at me here, but I would say that you could go from this step right here I can go from that step all the way down to my answer in one fell swoop. How do I do that? Well, when you're solving for y prime, just anticipate where you're going with this. You know the process of pushing all the non-y prime terms on one side. Those always end up in the numerator, right? So we could just collect all of the terms that don't have y primes in them in the top, and then every other term, after we factor a y prime out, that's all going to get divided to the denominator. So we can see that I'm going to end up here with a 6xy is one term in the bottom, minus a 2x squared is in the bottom, plus a 12y squared. That's going to end up in the bottom because that's a y prime term. See what I'm saying? So you really could jump right to the answer there without even having to show all that work. Okay. All right. Okay, I want to go back. How much time we got? Ooh, okay, not a ton. So I do want to go back and show you something here that's kind of cool. I want to just walk you through a really quick way to come up with the derivative rule for logs, which we already know, right? You've watched the videos, you know that the derivative rule for logs, the derivative with respect to x of log u is just u prime over u, right? So can we come up with a quick way of doing that? That would be sort of difficult to come up with unless we have access to implicit differentiation, which we now do. Okay, so let's kind of walk through this. So if we want to differentiate y equals log u, well, we can do that. Well, even without knowing the log derivative, we could just rewrite this as an exponential first of all, right? So this is a base e log. So I could rewrite that as u equals e to the y. We already know the derivative rule for exponentials, right? So what if I were to differentiate this implicitly with respect to x? What am I going to get? What am I going to get on the left side? What's the derivative of u with respect to x? Madeline?
Would it be like u? It has a u prime, right?
U prime. There you go, right? That's going to be a u prime, isn't it? I'm going to get a u prime on the left side. And then if I differentiate implicitly with respect to x on the right, doesn't that make sense? I'm going to get the derivative of e to the hand is e to the hand times hand prime, right? So the derivative of e to the y is e to the y. If I look inside that, the derivative of y is y prime, isn't it? Right? So now if I just solve for y prime, I get y prime equals u prime over e to the y. Well, remember, y is defined as log u, right? So e to the log u, the e and the exponential function and the natural log cancel out, and I just get a u on the bottom. So I get u prime over u. How about that? Okay, and then I don't want to spend a ton of time on this part of it, but remember there was another, in the videos it talks about there's another form of this. You know that the derivative with respect to x of the log of the absolute value of u. And sometimes that's important to use because the argument of a log function has to be positive, right? You can't plug 0 or a negative number into a log function. It'll explode. We know that that's equal to u prime over u. And so this also works. If you just wanted to prove this to yourself, this also works if we rewrite the function as y equals the natural log of the absolute value of u. And I'll just leave this up here. I'll let you guys walk through that. Anybody that's interested, you can kind of walk through that algebra. But it's not a big deal. It works both ways. Okay. All right. So see if we can get in. Okay. This would be the other thing I want to do. Yeah. Skip that for now. Let's do this one. Okay. Second derivative. We're not going to get through this. We're not going to have time. Let's just go back to this. This is really easy now. The question that we started the day with, if z equals x to the y, what's dz dt equal to? Think about that one. So this is a case where I'm differentiating implicitly with respect to t, right? To get a dz dt, I'm differentiating everything with respect to t. Well, the left side just gives me dz dt, or z prime, let's call it. What about the right side? What do you think, Natalie? How am I going to deal with the right side? It looks like a product to me.
Would it just be like x prime
Okay, so x prime times
y?
Okay, good. Let's do it the other way. Let's do x y prime plus y x prime. That's what you're going to say, right?
Yeah.
Okay. So there it is. And the primes just mean derivatives with respect to x. Okay. All right. How we doing on that stuff? Give me a 1 to 5. Okay. Good. It takes, we covered a lot of ground. It takes a little practice. So we didn't, the first assignment, I didn't quite get through everything I wanted to, but I mean, I don't know how I ever could have gotten through more than that. That was a lot. The first assignment does ask you to do in Math Excel, and I'll adjust the due dates a little bit. The first one asks you to do some derivatives, implicit derivatives involving second derivatives. Don't even try those until we go through an example or two. Okay, I'll put the assignment up, but don't try any second derivative ones. You'll just waste a bunch of time. We'll go through that first thing next time, and but you can do most of it. Most of it you can handle. Okay, sound good? All right. Have a great day. I will catch you later.